Okay, thanks for a very kind introduction. I would like to express my gratitude to Professor Wei for her nice invitation and the Faculty of Science for organizing this event. I feel very honored. So without further delay, let me start my presentation. My topic is about interquantile smoothness in censored quantile regressions. This is a joint work with my supervisor, Professor Tony Sitt. So quantile regression has become an effective tool to model survival data and handle data heterogeneity. Although there are many new proposals in this area, the non-smooth components involved in the estimator would result in unstable estimates, unnatural interpretations, and unreliable conclusions. In this work, we propose an estimating equation based approach to obtain a consistent estimators to the coefficient via induced smoothing. We also extend the method to handle functional data. We also propose an efficient resampling procedure in addition to a bootstrap-based method to improve computational efficiency. So what is quantile regression? Basically, it models the conditional distribution of the response variable given the covariates. For example, for fixed tau between 0 and 1, the linear quantile regression model specifies that the tau's conditional quantile of y, the response, is linearly related to z, the explanatory variable, or say the covariates. To estimate this model, we use the least absolute deviation approach which minimizes the check function in the following form, and the rho here is the quantile check loss function for quantile tau. Why we care about quantile regression since we already have the mean-based regression technique? There are three reasons. Its first advantage is the robustness to outliers. Suppose we have a simple model with the error terms given by the Cauchy distribution. Then you can see that in finite sample cases, the traditional linear regression on the left-hand side would never give a constant estimate for the coefficient, while the quantile regression on the right can recover the true model. Second, quantile regression can handle data heterogeneity. Consider this second model where the error is associated with the covariate. It is clear that the variance of the residual is changing with the covariate, and in that case, linear regression cannot work. The third advantage is the comprehensiveness. It means that when you obtain the conditional quantiles of a random variable, then you can build the whole conditional distribution of it. So it offers more insights compared to the linear regression model. In censored quantile regression, moreover, we need to handle situations with survival data. There are some special issues related to survival data, including the right censoring and the left truncation. I use this figure of movie actors to illustrate these two issues. So right censoring means that the observation is terminated by some external event like the end of the study. So in the middle figure, we can see that we stopped the observation in around 2001, and we only know that the actors were alive at that time, but we did not know when they exactly died. Left truncation means that individuals need to live long enough to be recruited in the study. For example, in the third figure, you need to live long enough to get nominated to the Oscar Prize, so you are in the observation pool. Ignoring these issues will lead to bias. There are several seminal works in the literature to handle censored quantile regression. When the censoring is fixed, or it is a no independent censoring, Powell's two works can help. If the censoring is unknown, but it's still independent of the survival time and the covariate, Ying and others discussed the median regression, and Peng and Fine discussed it under the context of competing risks. Under conditional independent censoring, Quantile proposed an estimator based on the self-consistency of the Kaplan-Meier estimator, and Peng and Huang proposed a martingale-based method. We will focus on Peng and Huang's estimator in our talk. So, to motivate our proposal in interquantile smoothness, we consider the HMO-HIV data. Using Peng and Huang's method, we will obtain the quantile models at these three quantiles, 0.5, 0.498, 0.507. Since these three numbers are very close, we would expect that these estimated models are close to each other. But is it really the case? The answer is no. So if we are given a subject with age 40 and drug use equal to 1, then the median of the survival time given by these three models can differ up to 0.5 months. And overall speaking, for patients on the median level of risk, the effects of age given by these three models can differ by more than 10%. Well, you may say that we have confidence intervals, and that is not a big deal since those confidence intervals would take into account those uncertainties. Well, a yes and a no. So as will be illustrated later, such instability of estimates can cause some problems in the statistical inference. Now let's go to our model. We have the notation for the event time T, censoring time C, covariate Z, the observed time, which is the minimum of the event time and the censoring time, the censoring indicator, the CDF of the event time, denoted by big F, the counting process of the failures, the at-risk process, and the cumulative hazard function. Notice that we can only observe X, delta, and the covariate Z. So it can be verified that the process MT given by this formula is indeed a martingale, so it has expectation 0. Based on this fact, we use a transformation of the time scale, and then we obtain the following martingale-based estimating equation. So we use the monotonicity of the quantile function and the basic property of it. We express the cumulative hazard function as an integral under the global linearity assumption. Then we plug it back and get the estimating equation 3. So Peng and Huang proposed to estimate the parameter on a fine grid S. They define the estimator as a right continuous piecewise constant function that jumps only at the grid nodes, and the corresponding values are obtained sequentially by formula 5. So starting at quantile tau 0 equals 0, we can get the estimates at quantile levels tau 1, tau 2, up to tau u. Now, our proposal. We let V be a multivariate normal random variable with mean 0 and covariance matrix I, the identity matrix. We let sigma be another positive definite matrix with norm of order big O 1 over n. And it will be serving as a working covariance matrix for our estimator. So we define the induced estimating equation as the expectation of the original estimating equation proposed in Peng and Huang with the parameter perturbed by a properly scaled multivariate normal random variable. Then we will have formula 6 for our proposed estimator. We will name our estimator the secret estimator. And it can be defined on the same grid, and the estimates are obtained by Newton's algorithm. We also generalize our proposal to handle functional covariates. In Jiang and others' paper, Then consider the functional linear relationship that incorporates the functional data UT, which can be translated to the quantile function 7. Here, the coefficient alpha is approximated by splines with order R, and the functional covariates can then be transformed to some non-functional ones using the basis function of the splines. Then the question reduced to the linear quantile regression we care about. So similarly, we applied the perturbation and the expectation, and then we can get the estimating equation 9 for handling functional data. We need to show our proposed secret estimator is good, so we need some asymptotic guarantees. But I would like to skip this notation, conditions, and go directly to the results. So they basically say that the secret estimator is consistent and is asymptotically normally distributed. A more interesting topic would be the inference approach in finite samples. We give 2 approaches. The first one is the standard multiplier bootstrap method, and the second one is the efficient resampling method tailored for our secret estimator. The idea behind the multiplier bootstrap is simple. We add some perturbations to the original estimating equation with mean 1 and variance 1, and then we solve the equation. The confidence intervals can then be constructed using normal approximations or by referring to the empirical percentiles of the bootstrap samples. We refer to the variance estimator obtained by L1 minimization as MB and by Newton's method as MBIS. The second approach we propose is based on an expansion to the asymptotic variance expression for the estimator. So the expansion is here, and we replace the unknown quantities in this expansion by the sample analogs, and then we are done. So in step 1, we take the derivatives of the corresponding smoothed version of the target functions, and then obtain the matrix MK. Second, we approximate the distribution of our estimating equation again by perturbing with mean 1 and variance 1 random variable. So as the theoretical guarantee is presented here. Third, we plug in and obtain the bootstrap samples. We name this approach as variance for the IS approach. Some more intuitive explanation by simulation study. We generate the event times according to this model, and the censoring rate is approximately 20%. Here is the simulation results. We can see that the pH and our secret estimators are both unbiased, with MSE close to 0. However, regarding the interquantile smoothness, which we use the local total variation and the local convexity to measure, the secret estimator demonstrates significant improvements over the pH estimator. So right. As you can see, the improvement can be up to 90%. In terms of variance estimations, all methods are good, and the empirical coverage is close to 95% nominal level. A graphical illustration, we can see that its secret estimator is smoother and it can achieve good MSE reductions. The variance estimations are good, except that the MB approach is a bit inflated. So go back to our data analysis in the motivation. The covariates here are the centered age and the prior drug use. We show the regression results at tau equals to 0.3, 0.5, and 0.7 in this table. And as we can see that these 2 estimators are fairly close to each other. When we look at the whole quantile process, we see that the age and drug are both negative indicators of lifetime. However, the pH estimator is fluctuating while the secret estimator is very smooth. Also, the confidence intervals of a pH estimator is wider than those of the secret estimator. More seriously, when you look at the drug effect at 0.25 quantile, the pH estimator would say that the effect is significant here. But you do not know whether it is due to the sudden jump of the estimate or it is a real significant effect. That would be misleading, right? So summary of the our data analysis. And I would like to skip the next two data analysis, but I would like to emphasize that the pH estimator is in general very fluctuating, while the secret estimator is smooth. So a summary, we propose a class of linear quantile regression models for survival data subject to conditional independent censoring, and it enjoys interquantile smoothness and MSE reductions. Numerical results shows that our proposed estimator is better than the plain estimator in the literature, and we recommended that it serve as a benchmark for smoothness and MSE reductions for subsequent developments. Okay, two possible directions for to extend our model, and I will skip here as well. So my talk ends here. Thank you for your attendance and your attention. So now question from are invited from the audience. Thank you very much for listening.
Thank you, Mr. Tsai. We have received two questions in the chat room, so perhaps you may switch on the chat room and refer to them. So there are two questions. The first one is, what if the censoring is interval censoring? And the second question, do you assume non-informative censoring? Mr. Tsai, please.
Okay. Thank you, Professor Song, for your question. So for question one, if the censoring is interval censoring, I think there is also a paper discussing this kind of situations. I think it's proposed in 2016. There is also another paper discussing it, and it is definitely possible to handle interval censoring. We indeed put it into the appendix, and yes, so the basic idea is that if you have a left censoring and right censoring, you can construct an indicator such that the left censoring variable and the right censoring variable are there, and then we can apply the same induced smoothing technique to that term, the indicator term, and transform it to a smooth one. So yes, it is possible. And second one, non-informative censoring. We assume that the censoring indicator is independent of the event time conditional on Z. So I think, yes, currently we assume this non-informative censoring. However, it is still possible to consider other situations, like I think in these bias sampling schemes where the censoring time might be indicative, maybe informative, it is still possible for handling those situations, and it is a future direction for extension. So do I answer your questions? Okay, thank you very much.
Thank you, Professor Song, and thank you, Mr. Tsai. Do we have any question from the audience at the venue? All right, if we don't have further questions, thank you, Mr. Tsai again, and let's welcome our next speaker.
Okay, hi everyone. I'm Rongqian from the Department of Statistics, and my topic today is based on causal mediation analysis with latent mediators and the survival outcome. This is a joint work with my supervisor, Professor Xingyuan Song, and my senior fellow, Xiao Zhou. So let's begin with some basics of mediation analysis. The simplest mediation model comprises an exposure, a mediator, and an outcome, where we care most about to what extent effects of the exposure is implemented through the mediator. This problem is of more interest in psychological and biomedical researches to identify the underlying mechanisms of certain behavior or disease. And a classic way of mediation analysis is to regress the mediators and the exposure, and then regress the outcomes on the other two. But a problem is, even if the mediating process itself conveys a causal chain conceptually, what we obtain from regression is actually more or less correlation rather than causality. So in the past decade, mediation analysis is extended to the counterfactual frameworks to combine with potential outcomes. Here, if we have a binary exposure AI, and MPhil of AI is the potential values of the mediator. Suppose the exposure is set to the level of 0 or set to the level of 1. And similarly, yi of small a and small m is the potential value of the outcome. Suppose the exposure is set to the value of the level of small a, and the mediator is set to the level of small m. So based on these potential outcomes, we can derive our causal estimates of interest. So loosely speaking, this yi1 here is like the pain rating of a patient. Suppose he had to take certain medicine, and yi0 is like the pain rating of this same patient if he had not taken this medicine. So intuitively, differences between these two potential values are the individual total effects of this medicine or this exposure, and it does have a causal interpretation intuitively, right? Because it is of the same person at the same time. So now, if we control for the mediator, then the differences between these two potential values is the individual direct effect for this person. And if we controlled for the level of the exposure, then difference between the two potential values is the individual indirect effect of this person. But in practice, these two potential values can never be simultaneously observed because they are of the same person at the same time. So actually, we are modeling the average causal effects and a certain sequential ignorability assumptions that will be mentioned later. And then in survival analysis, models with multiple parallel or causally ordered mediators has been proposed to assess the causal effects on various scales. Here, parallel means the two mediators are causally non-ordered, like the mediator 1 and 2 here in this path diagram. And by causally ordered, we mean there is a directional path between the two mediators, like mediator 2 and 3 here. And our work extends this model to accommodate latent mediators, which are an observable dimension that has to be measured from several aspects. And this idea is motivated by the Alzheimer's disease neuroimaging initiative study, where comprehensive types of data are collected to track the pathology of the Alzheimer's disease. According to medical background, we see this APOE epsilon 4 allele is closely related to hippocampus atrophy, ventricle expansion, cognitive impairment, and finally to dementia, or AD. Hippocampus and ventricle volume are directly measurable, right? And they're further related to cognitive impairment. But cognitive decline is a latent trait that cannot be directly observed, and it has to be measured from several aspects like language using, memory, and attention. So in this case, our exposure of interest is the number of these APOE epsilon 4 alleles, and the 1-year difference in hippocampus and ventricle volume are two observable parallel mediators. The cognitive impairment is the latent mediator denoted by M and measured by 3 observable test scores, ADS-11, ADS-13, and MMSE. So higher values of the first two and lower values of the last indicates poor cognitive ability. And our outcome of interest is the time to dementia or time to AD. And the ultimate goal of this analysis is to simultaneously achieve the measurement of the latent mediator and the estimation of the path-specific causal effect through a joint modeling approach. So the first part of our model is a linear structural equation model, where the first equation measures the unobservable latent mediator M, and the other two captures the relationships between the exposure, as here, and the mediators W and M. So the coefficient matrix alpha and beta here will be used later to construct the causal estimates, as we mentioned before. And the second part of this model is a common proportional hazards model in survival analysis And these major notations has just been introduced by Zexi just now. So in this equation, the unknown baseline hazard lambda 0t is treated as piecewise constant in our analysis. And the regression vector gamma will also be used to construct causal estimons. So this is a general visualization of the proposed model. Recall that we have causally ordered mediators W and M, and the exposure S can affect the log hazard of this disease, Alzheimer's disease, either directly or through the mediators. So as mentioned before, we need some assumptions to identify and express the causal response in the parameters of the model we have just proposed. The stable unit treatment value assumption is frequently used and a common assumption in causal inference. And the set of these unconfoundedness assumptions actually stated that there is no unmeasured confounding between the exposure and the mediator and the outcome, and the exposure and the outcome. So under these assumptions, we can actually identify the causal estimons or identify the potential values or the counterfactual log hazard function, this log lambda here, in a closed form as proposition 1 closed. So based on these counterfactual log hazard function, we can express our path-specific causal effects as difference between certain two potential values. Like here, delta from S to T is the direct effect of this exposure S. As we can see here, all the mediators are fixed at certain levels, and only the level of the exposure is allowed to vary. And delta from S to MK to T is the indirect effect that is implemented through only the kth latent mediator MK. Again, the exposure and all the other mediators are fixed, and only level of this kth latent mediator MK is allowed to vary. Okay, so in our case, this is actually the indirect effect implemented through only cognitive impairment. And next, delta from S to WKT is actually the indirect effect implemented through the kth parallel mediator, which in our case might be the hippocampus atrophy or ventricle expansion. And as to the bold WT is the indirect effect implemented through all the parallel mediators together. So these are our path-specific causal effects of interest. And for model estimation, we assign conjugate priors to the parameters in our proposed model, and then obtain posterior draws by MCMC algorithms. So for sake of time, we don't talk in detail here. And next, estimation accuracy of our method and its sensitivity to certain non-normal errors or different prior inputs is checked through simulation study under different settings. Here we just put part of the result here to illustrate that the bias and root mean square error at the observed causal effects estimates is relatively small compared to its true value, and the performance is improved when the sample size gets larger. So we now go to the application to ADNI data. Recall that we have two parallel observed mediators, hippocampus atrophy and ventricle expansion, and one latent mediator, the cognitive impairment here. And the survival curve on the right clearly stated that people with more APOE epsilon 4 alleles has actually poor survival probability. The red curve is for people carrying no APOE epsilon 4 alleles, and the blue one is for people carrying 2 APOE epsilon 4 alleles. So we then have our path-specific causal effects of this APOE epsilon 4 allele on the hazards of AD. Here, as we can see in the last, the results of our method is put on the left part. And from the rest row, as we can see, for people carrying one APOE epsilon 4 allele, the hazard of AD is e to the power of 0.789 times of those who, who does not carry this allele. And more specifically, this hazard is increased directly by e to the power of 0.486 times through cognitive impairment only by e to the power of 0.075 times, and through the two parallel mediators together by e to the power of 2 to 8 times. So to show the necessity of accommodating latent mediators, we can make a comparison to the way that ignore the latent mediator and directly employ its three surrogates as observed mediators. The results are put on the right. Here we can see the effect through ADS11 becomes negative and insignificant, while the effects through MMSE becomes positive. This contradicts the reality that higher values of ADS11 and lower values of MMSE actually corresponds to larger hazard of AD. And for people carrying two APOE epsilon 4 alleles, the effect estimates are of the same sign, but with larger size. And these problematic estimates of ADS11 and MMSE also appears. So in conclusion, we have found that ignoring the latent mediators and using one of or all its surrogates as observed mediators may misinterpret the mediating mechanism and produce some misleading results. So that's why it is necessary to incorporate the latent dimension when it truly exists. And finally, there are some possible extensions of our method, like the doubly robust estimation and some heterogeneous causal mediation effects. So finally, I would like to thank my supervisor, Professor Qian Song, and our group members for their support. And thank you for your attention. Any questions are welcome.
Thank you. We have received some questions in the chat room. Okay. Oh, two questions now. The first one is, how do people usually determine the order of the parallel mediators? And the second one is, in practice, how to verify the sequential ignorability assumptions?
Okay, let us start with the first one. How do we determine the order of the parallel mediators? So actually, the parallel mediators themselves do not have orders because they are causally unordered. And the order exists between the parallel mediators and the ones that are causally ordered to them. In this case, we may have to use some background knowledge, like in our case, the medical researchers and some clinical knowledge tell us that the atrophy of hippocampus and the expansion of ventricle is related to cognitive impairment. And intuitively, we know that it is more possibly that hippocampus atrophy and ventricle happens first, and then cognitive impairment happens. So usually we may rely on some prior knowledge to determine the order of the parallel mediators, and there's ones that are causally related to them. So, and the second one, how to verify the sequential ignorability assumptions. Okay, these assumptions here may seem some restrictive, but in practice, we will usually put all the covariates we have into the model, even if sometimes we may have to do some variable selection. But once we put all the background covariates we have into the model, it is more plausible that there is no unmeasured confounding that will violate the sequential ignorability assumptions that we proposed. Although it cannot be theoretically verified, but it's somehow solved by including all the covariates we have into the model. So do I answer your question?
All right, any question from the audience at the venue? If no, thank you, Ms. Wan again.